So this is it, the last video of the year. How fitting that it should be about proofs. All right, let's get this job done. More circle proofs. In number 1, we're told that segment AC is tangent to circle O at point A and tangent to circle P at point C. And we might have some dilemma or some difficulty about marking this in the diagram, but if we do, it's helpful to remember that wherever a tangent meets a radius, as you see going on here when tangent AC meets circle O, and we have going on in the second circle where tangent AC meets circle P, a tangent that's drawn to a radius is always going to be either perpendicular or form right angles. So now those right angles that are at A and C are going to be congruent to one another. Notice that they're alternate interior angles for the red segment OA and the blue segment CP. And if the alternate interior angles are congruent, we know from our work with previous units that those lines have to be parallel. And now if we think about segment OP as being the transversal for those parallel lines, that's going to make the angles at O and P congruent because they're alternate interior angles on parallel lines. So this is a really nice proof for the last unit of the year because it takes into our account our work with circles, but also our work with parallel lines. So again, that's going to be kind of the gist or the direction of my proof. I'm going to talk about the right angles being congruent, them being congruent alternate interior angles, forcing the lines to be parallel, the parallel lines forcing the alternate interior angles at O and P to be congruent. All right, so let's go ahead and let's get started putting this into words. Segment AC is tangent to circle O at point A and to circle P at point C. We know that's a true statement because it's given to us to be a true statement. And I can see in the picture that that tangent is drawn to the radius. And because that tangent is drawn to the radius, that makes the angles at A and C, which I'm going to call 1 and 2, right angles. And that's because anytime we draw a radius to a tangent in a circle, it makes a right angle. The fact that both of those are right angles makes them congruent. So now my next statement, I'm going to say that they're congruent to one another. And that's an oldie but a goodie. It's one that we all know and are familiar with. And if angles 1 and 2 are congruent to each other, they're alternate interior angles now for the green lines. That makes the green lines parallel to one another. So this tells us that either line OA or line segment OA must be parallel to line segment PC, because anytime we have congruent alternate interior angles, it makes our lines parallel. And now that those lines are parallel to one another, I'm going to think about the purple segment as being a transversal. Anytime we have line segments that are congruent, that makes our alternate interior angles congruent. I'm going to name them, for lack of something better, angles. Oh, I can't name them. I wanted to, but I can't. They've already named them for us. So that's going to make angle O congruent to angle P. And again, anytime we have parallel lines, that makes our alternate interior angles congruent. All right, good job. Well done on that one, folks. Again, if you have questions or concerns, write them down. We'll be more than happy to discuss them the next time that you come back to class. But in the meantime, we're moving on to the last and final proof. All right, This one says we're given this circle O with a diameter AC that it's extended through C to D in such a way that the segments are perpendicular. And they very nicely have marked that for us in the picture. And we're trying to prove segment AF times segment EC is equal to segment AC times segment FD. Remember from our unit on similar triangles that anytime we see these numbers being multiplied together, the only way that we can achieve that, or the only way that we can get that, is through similar triangles. So whenever you see products, you always want to think similar triangles. And this is great review going into the Regents exam. And you might say, well, what triangles is it that we want to make similar? Well, AF has to be a side in one of our triangles. So that pretty much tells us right off the bat that one of those triangles is going to have to be the large blue triangle. EC must be a side in one of our triangles. And the only triangle with EC as a side is going to be that red one. So our mission or our goal is to make or prove the blue triangle similar to the red triangle. Well, just by looking at the picture, I can see that we have a shared angle there at A. So that's going to be one pair of angles. I'm going to need a second pair. I'm noticing quickly that this angle at D is a right angle because it's been marked such at in the picture. And I notice that angle E in the red triangle has to be a right angle as well because he's inscribed in a semicircle. His arc is arc AC, which is a semicircle. So those two triangles are going to be similar by angle-angle similarity. And again, I'm going to use the shared angles at A along with the right angles that are marked in the picture to prove them similar. All right, I think I'll save the reflexive property for the end because that's the easy piece, and I'm going to get right down to work on the harder piece, and those are the right angles. So segments AD and DF are perpendicular. We know that they're perpendicular because they're given to us that they're perpendicular. And those perpendicular segments are going to make right angles. So I'm going to say angle 1 is a right angle. And that's because the perpendicular segments or perpendicular lines form right angles. The other angle I know that is a right angle is angle 2. And that's because any angle inscribed in a semicircle is a right angle. Now I can go ahead and say angle 1 is congruent to angle 2. We know that all right angles are congruent. All right, our other angles were the angles at A. I'm just going to call them angle 3. And that's by the reflexive property. It's the same angle in the red triangle as it is in the blue triangle. And putting together the right angles with the reflexive property angles, we can now go ahead and say that our triangles are similar. We do have to be very careful when we name the triangles. The first triangle I'm just going to call triangle ADF. The second triangle I'm going to have to be a little bit more careful. In the red triangle, the angle at A matches up with the angle at A. But I want the second angle to be the right angle because the second angle in my first triangle was the right angle. So triangle AEC. And again, just make sure you match up those corresponding parts. This is great review moving into the Regents exam. So angle-angle similarity. Once the triangles are similar, we know that their corresponding sides are in proportion. So we can go ahead and we can use those similar triangles to write a proportion. So we want to put AF and EC opposite so that when we cross multiply, we'll get their cross product. AF in the big triangle is going to match up with AC in the little triangle. And that means FD has to go here in the ratio with EC. And this is a reason we haven't used in quite a while. Anytime we have similar triangles, they have corresponding sides that are proportional. And then lastly, to wrap it up, I'm going to go ahead and cross multiply that proportion. So AF multiplied by EC is going to be the same or equal to AC multiplied by FD. You could say the product of the means is equal to product of the extremes. I'm going to be a little bit more simplistic and just say the property that I'm using here is cross multiplication. Well, that was a great proof to end things on. Like always, I'm going to have you flip up to the top of the next page, see if you can apply what you've learned to solve that last and final check your understanding problem, with the idea in the back of your mind that if you need to ask questions, you can feel free to do that the next time you come back to class.